Hi, I'm Hassan, the lecturer here at the Institute of Medical Education, and today we're going to take a look at solutions to Section 3 of ACER's GAMSAT Green Booklet, Practice Test 1, specifically Unit 9, questions 28 to 31. And in this unit, we're looking at how a moth raises its temperature of flight muscles in its thorax in order to fly. And we're showing Figure 1 of different initial resting temperatures and how well, I guess, the moths can increase the thoracic temperatures at these initial temperatures. It's pretty obvious we can see that the rate is greatest with a higher starting initial temperature, so the rate of thoracic temperature increasing is higher. But just before we move into the graph, let's just take a quick look here on my figure here about how we can actually read graphs for their rates of change and determining the rate from a graph. So it's important to know when we see, say, gradient equals 1, what we're saying is that y equals 1. So if y equals x. So if y equals 1, x is going to equal 1. Y equals 2, x is going to equal 2. So the gradient is going to equal 1. So it's a nice linear curve and it has a nice property. Now, say we change this property and say y is going to be equal to greater than x. So let's say y is 2, x is 1. So you can see that the gradient is going to be steeper because our y value, let's say our y value is 2, x has to be 1, y is 4, x has to be 2. So you can see that as the slope gets steeper, the y value increases, I guess, larger than the x value. But if we flip it and go to the other side where the gradient is getting lower, you can see that the x value is getting bigger. So let's say 2x equals 1y. So you've got, say, 2x, 1y. It just keeps getting bigger, the x value, whereas the y doesn't change as much. So that's how we say that the gradient is going to be less than 1. So you all are probably aware that a change in y over change in x, or y2 minus y1 over x2 minus x1 is important in identifying gradients. I mean, it's probably not that important to use it for this figure here, but for future exams and future GAMSATs, please remember this when reading graphs in terms of ascertaining the rates of change. So if we take a look at the first question, 28, it says, for which of these initial temperatures has the greatest increase in thoracic temperature per minute? So if we take a look at the x-axis on figure 1, we go to 1 minute. We see clearly that it has to be initial temperature of 30 degrees. You can clearly see it anyway because the rate of change is the greatest amongst all other initial temperatures. And also you see it increases by about 7 degrees in 1 minute, whereas the rest are less than 7 degrees. I think the next best would be the 25, which is about 6 degrees, initial temperature of 25 degrees. And you've got, I think the least initial temperature of 15 is only about, let's say, 2.5 degree change. So the answer for 28 is going to be D. So if we go to question 29, 29 states consider the initial temperature of 20 degrees. In the first 2 minutes of the following, the heat loss is most likely to have been. So straight away, we've only been told in the stimulus about the thorax. We haven't been told any information about the abdomen. So we can eliminate C and D straight away. So the answer is going to be A or B. So it's important to know, if we take a look at 20 degrees here, it's a nice steep increase in the slope. So you know, if it's a steep increase in the slope, you know straight away that the heat being produced, the heat that is lost, if I read this correctly, yep, so the heat lost from the moth's thorax has to be less than what's being produced. Because if the slope is going to be great, so look, see here, it's greater than 1. If the slope is greater, that means you're not losing much heat, you're producing more. If the slope was a bit flat like this, you'd say that it's losing heat. However, because the slope is obviously greater than 1, you can see that clearly. You know straight away that the heat lost has to be less than the heat produced in the thorax. So it can't be equal. If it was equal, then gradient would equal 1. but the gradient here clearly doesn't equal 1. And you can do the change in y over change in x to find out the rate, but I mean, you can just eyeball it and you can see straight away. So the answer for 29 has to be B. So now if we move on to the next question, so it's included a new, I guess, additional information. It's talking about oxygen consumption of bumblebee queens for involved in, I guess, incubation of their broods or their progeny at different ambient temperatures. Now, if we take a look at question 30, this is something I like teaching my students, is that please, whenever you're looking at a graph, read it carefully. Don't make inferences from graphs. If it's not explicitly stated on the graph, don't make an inference. Because all we're told in this figure, in figure 2, is the y-axis is rate of oxygen consumption, so the metabolism, pretty much, over the ambient temperature. So the metabolism is changing over temperature, different temperatures. So we can't make the assumption that because the ambient temperature, in this instance, you can see the slope is negative. So the slope is going down, so there's a decrease. So you know straight away that it's going to be a decrease in rate. But you can't make the assumption that because there's a decrease in the rate of oxygen consumption, that means there has to be a decrease in the either anaerobic or aerobic respiration or whatever it is. So you can't make that inference because all we know from this graph is that metabolism is decreased. The rate of oxygen consumption is decreased. What happens downstream of that, we're not told. So we have to just answer what the graph is telling us. And the graph is clearly telling us that the rate of metabolic respiration is decreasing. So the answer for 30 has to be C. So now if we go on to the last question, it's kind of why I included this section here. It states at 10 degrees, so straight away look at figure 2. At 10 degrees, that corresponds to 120. So let's go straight away. So it corresponds to 120 mils O2 per hour per gram. So that's important to know. So it says at 10 degrees, oxygen consumption each minute in 0.2 grams bumblebee queen thorax. So we're told we have to find out what it is per min per 0.2 grams. So if we're going to try to figure this out, let's just start off first with the easy one. So 120 in 0.2 grams. So if we're told here that this is 120, so at 10 degrees, we've got 120 mil of oxygen per hour per gram. So we want 0.2 grams. So 0.2 grams is a fifth. So therefore, what's a fifth of 120 mil? So, I mean, in your head, you can probably think of it, the way I thought of it was, let's go up to 240. So 240 is double. So if 1/5 of 120 is going to be 1/10 of 240. So if you just use that arithmetic, therefore it's going to be, so 1/10 of 240 is 24. So 24 mils in 0.2 grams, but it's still per hour. So now we've got to convert it to per hour. So what we do there is we divide it by 60. So 24 divided by 60. So let's just say 24 divided by 60 is going to equal, so 24 mils divided by 60. So you know straight away, if you do some quick mathematics, it's going to be, so let's say 30 divided by 60. So in the GAMSAT, you don't have much time. So let's say it's going to be 30 divided by 60. So it's around 0.5. You know, it's just a bit less than 0.5. So it has to be somewhere just a bit less than 0.5. But if we take a look at our answers here, 31, the only correct answer has to be D, because the answers provided are wrong there. So the answer is around 0.4 mils per 0.2 grams per minute. So that's your answer. So please, when you read the axes, read the units carefully. So if you have any questions about this unit, please post them in the comment section below. Or if you want to contact us directly, please do so. We'd love to help you. Thanks for your time. Bye now.